Hello, this is Dr. Gardner. We're continuing our discussion of Chapter 2. Today we'll be looking at atomic mass and how that relates to relative atomic mass on the periodic table. In our previous video we had looked at using the periodic table to classify elements, but we'll take a few of those ideas and apply them today as we start looking at the types of ions that form and how we can predict their charges. We'll also look at how we can predict the formulas of ionic compounds when cations and anions combine to form neutral ionic compounds and their ionic lattices. So that's our plan for today. I wanted to do a few review questions, so feel free to pause some of these review questions and try to answer them before I give you the answer to them. That will help you practice to see if you could answer these types of questions on our exams. So our first question is looking at the following atomic symbol. Now I should recognize that that element is chlorine. We want to predict how many protons, neutrons, and electrons are present by looking at this atomic symbol. Now in this case, you should be able to recognize that the atomic number is 17 and the mass number is 37. So from that information, you want to decide how many protons, neutrons, and electrons you would have. Okay, so go ahead and pause this if you would like, and then I will help you work through the problem. Okay, so chlorine has an atomic number of 17, and the identity of an element is determined by its atomic number, which is identical to the number of protons in the nucleus. So the only answers here where we have 17 protons would be answer B and C. Okay, now we have a neutral atom here. I know that because the upper right hand superscript is normally where we would show charge. Now if we have zero charge, we frequently won't show zero in that superscript. We'll just assume if it's not shown, it's a neutral atom and it has zero charge, meaning that it has not gained or lost any electrons, but it must still have the exact same number of electrons as the number of protons in the nucleus. So I must have 17 electrons. Well, we still have choice B and C because they both have 17 protons. The neutral atom has 17 electrons, but we need to decide how many neutrons we have. If you had picked C, that is incorrect, unfortunately, because my mass number isn't equal to my number of neutrons. My mass number, which is 37, is equal to all of the subatomic particles in the nucleus involving protons and neutrons. Okay, the mass of the atom is primarily determined by the number of protons and neutrons. The electron's mass is so small, we're ignoring it for the sake of determining mass numbers. So if I take 37 and subtract 17, you're going to see you would have 20 neutrons in the chlorine 37 isotope nucleus. So B was the correct answer here. Now here we're looking at another element symbol. Now this one is further down the periodic table, so I would like you to learn the identity of this element and its symbol if you haven't already. The symbol W stands for tungsten. Okay. Now there's something slightly different by looking at this atomic symbol. I haven't given you the atomic number, but I did give you the mass number. So you might want to ask yourself, can you still solve this problem without it? I hope you said yes, you can solve this problem as long as you have a periodic table present. And you will always have a periodic table when you're doing homework. It should be in the back of your book. If you don't have that handy, hopefully you've printed a copy of the periodic table you use for reference. On all exams, you will be given a periodic table to use, so you should always have one. If I do go and look at a periodic table, that's going to help me find the atomic number. So I see that the atomic number for tungsten is 74. So I go to the periodic table to find that. So if I were to write the atomic number next to this symbol, I would write a left-hand subscript of 74. Now we should remember then how that helps us predict the number of protons, neutrons, and electrons. If you'd like to go ahead and pause the video and answer this for yourself, feel free to do so. Okay, so since my atomic number is 74 and that determined the identity of the element is tungsten, well, we must have 74 protons because the identity of the element is equal to the number of protons in its nucleus. So we have 74 protons in the nucleus of tungsten. If we have a neutral tungsten atom, which is indicated by no charge shown in the upper right-hand superscript, then we must have the same number of electrons outside of the nucleus with respect to this atom. So I would have to have 74 electrons. Okay, so right now I'm seeing B and D fits the bill, but I have to decide how many neutrons here. If you chose B, you are confusing the mass number here with the number of neutrons, which is not true. The mass number is derived from the number of protons plus the number of neutrons. Since I had 74 protons, if I subtract 74 from 183, I'm going to get a 109. So D is the best answer with 74 protons, 109 neutrons, and 74 electrons. Okay, let's practice another one. Let's consider if we were reading a textbook, uranium-235. If I see uranium-235, the name of an element followed by a dash and a number, well, hopefully we realize right away that this number cannot be the atomic number. That would be much too high for an atomic number for the elements that have been discovered on the periodic table. So that must be its mass number. So when you see an element name followed by a dash and a number like this, usually indicates the mass number for the element, even though we haven't written the atomic symbol. Now, I didn't give you the atomic number here because I hope you can already predict where we can find the atomic number. Hopefully you're thinking we can look at the periodic table. So let's go ahead to the periodic table. In the actinides, in the inner transition elements, we have uranium. Okay, its atomic number is 92. So hopefully that's going to help me determine the number of subatomic particles in my nucleus. So if you'd like to pause this question and try to answer it for yourself before I give you the answer, please do so. Okay, since the periodic table tells me the atomic number for uranium is 92, I know that's also equal to the number of protons in the nucleus of uranium, which is identifying the type of element we have. So we have 92 protons in the nucleus, so only A and B would correctly identify the protons. Now, we have a neutral atom here because, again, we have not given any information about charge. So we're going to assume it's neutral if no charge information was given. So it's a neutral uranium atom, which means I should also have 92 electrons. Again, we still have A and B as possible correct answers, so I'm going to go ahead and have to look at both of them to see which one is correct. And so if you take the mass number of 235 and go ahead in your calculators, you can do this. You can take 235 and subtract the number of protons, which is 92, and you'll find that you have 143 as the leftover mass. So I have 143 neutrons. So B would be the correct answer here. B would be the correct answer. Okay, so let's consider that we have an isotope of bromine. And I tell you this isotope of bromine has a mass number of 80. Now, if I have an isotope, remember that you can have several different isotopes of a single element. So bromine can have several different isotopes. That what differs with respect to isotopes is the number of neutrons in the nucleus. Their atomic number would be identical no matter the isotope that I have. If the atomic number differed, I would have different elements. Okay, so here I have bromine has a mass number of 80. I'd like to find out how many protons, electrons, and neutrons are in this isotope of bromine. So if I go ahead and look at the periodic table to find my atomic number, we see that bromine has an atomic number of 35. So there's my reference atomic number from the periodic table. So I know I have 35 protons, so A and B would fit the correct number of protons here. My mass number is 80. It's a neutral atom because I wasn't told anything about charge, so we're going to assume it's neutral. So I should have 35 electrons. Now I know my answer can't have 80 neutrons because the entire mass number is 80, and remember your mass number is the sum of the number of protons plus the number of neutrons. So if I subtract the number of protons, which is 35, from 80, we'll have 45 left over. That's the number of neutrons I have, so B is the correct answer here. Now, if I were to write the isotope symbol of the same bromine isotope you're looking at with the mass number of 80, which would be the correct symbol that you should have? Okay, you might want to pause the video here and see if you can answer this before you continue. Okay, so I need to remember where my numbers are with respect to mass number and atomic number here, and then relate that to which one of these symbols is correct. Now, my mass number is the sum of the protons and the neutrons. You were already given the mass number, so I know that the mass number here would be 80, and the 80 should be in the left-hand superscript. So either B or D would be correct based on that. And I know from my atomic number from looking at the periodic table that bromine has an atomic number of 35. Okay, so that would be In this case, that would be D. If you had put 45, you were confusing that with the number of neutrons we had seen before. So be careful. Also be careful not to show the number of neutrons for a mass number, because it's neutrons plus protons adding up to 80 that you should show for your mass number. So the best answer here was D. Okay, so we've been looking a little bit at atomic numbers and my mass numbers, as well as how to relate those to an atomic symbol to convey information about all the subatomic particles in my atoms. We also are seeing that if the number of neutrons vary, we start talking about isotopes. Now, when we have isotopes, you might want to ask, would their chemical properties vary? Would the chemical properties of isotopes vary from one another? So let's say we had an isotope of hydrogen. Hydrogen's most common isotope has a proton in the nucleus and no neutrons. Okay, that's a hydrogen 1 isotope. A hydrogen 2 isotope would have an additional mass number of 2, so its mass is increased by 1 compared to the hydrogen 1 isotope. That is because it's gained an extra neutron. The number of protons are not changing, or it wouldn't be the element hydrogen anymore. We would have gone to helium. So we must be adding neutrons as we end up with higher mass numbers for hydrogen. So if we end up with a mass number of 2 for the hydrogen 2 isotope, we actually oftentimes in the sciences refer to that as deuterium. Okay, so if I have compounds, chemical compounds that have formed by hydrogen combining with oxygen, we could form H2O, which is water. Or if I had the hydrogen 2 isotope, I could still form H2O with the heavier isotope. We often call that heavy water, though. Now, the two samples of water with respect to the heavy water or the water with the hydrogen 1 isotope actually have the same chemical properties. Now, here's the reason why. We did not change the number of electrons. We have the exact same number of electrons in the hydrogen 1 as the hydrogen 2 isotope. Okay. Sometimes we'll indicate the hydrogen 2 isotope in the sciences with a D. Luckily, we don't write all of the other isotopes in nature with different symbols, or that would be very confusing since you're learning symbols for so many different elements on the periodic table. So normally we wouldn't give another symbol to the same element's isotopes. But here we did. We gave it a capital D standing for deuterium. That's the H2 isotope of hydrogen, sometimes called heavy water. What we will notice, though, is their chemical properties are identical. They have the same freezing point, the same melting point. It's because the outsides of the atoms are identical. We have the same number of electrons. We have in the neutral hydrogen atoms 1 electron present. That hasn't changed whether I had an isotope. The only thing that's changing is buried down in the nucleus, the number of neutrons. Okay, so I don't change any chemical properties. My chemical properties are determined from my electrons on my outsides of my atoms as they're either transferred to form ions and form ionic compounds, or shared between nonmetals to form molecular compounds. So in this case, the chemistry is identical. Heavy water has the exact same chemistry as my hydrogen 1 isotope water, which is what we have mostly in nature, even though there's a little deuterium mixed in, but not very much. If we end up looking, though, at the physical properties, they do vary because the deuterium isotope, the hydrogen 2 isotope, is twice as massive per hydrogen atom as the hydrogen 1 isotope. So we can start to look at the density and physical properties like that we have here as being slightly different. So for example, if I were to put an ice cube made from the hydrogen 1 isotope in the form of H2O in a beaker of water, you would probably expect it would float, just like it would in a nice cold glass of water on a hot summer day when you put ice cubes in the water. You would expect it to float on the top. In fact, you'd be very shocked if that ice cube sank. But if I put an ice cube made from D2O, deuterium oxide here, dideuterium oxide, monooxide. The hydrogen 2 isotope that's present in the deuterium makes it dense enough that the ice cube would sink as long as the water in the container is made from the hydrogen 1 isotope. So the density is very different. So I can tell the top ice cube contains the lighter isotope, the bottom ice cube contains the heavier isotope, and in fact this is one of the methods we can use, these differences in physical properties, to separate isotopes from one another. For example, when they start to separate uranium to enrich it for nuclear power plants or nuclear weapons, they can go ahead and form compounds with uranium that are gases, and these gases have slightly different densities depending on the isotope of uranium that you have. So you can go ahead and use gas permeable membranes to separate them, or more likely we can use their density differences in gas centrifuges to separate out the different uranium isotopes gases and those compounds they have formed based on different densities. Okay, so they can use those types of centrifuges to separate out the uranium isotopes and enrich it for uses that we might have. Okay, so it's physical properties that allow you to separate isotopes, not chemical properties. They react chemically identically. In fact, if you were to ingest D2O compared to H2O, you would expect it to react identically with your body. However, the dangers of doing so is that the physical properties of the D2O are different. It will slow down chemical reactions in your body because of its higher mass. So the kinetics, the speeds of the biological metabolisms in your body and the biological reactions occurring would change. And this could result in, if you consumed a lot of heavy water, this could end up resulting in your demise potentially. Small amount of heavy water, you probably wouldn't know the difference because you'd have plenty of the lower isotope of hydrogen that your body would function just fine. The kinetics wouldn't change significantly. You don't have to worry about in our everyday lives consuming too much heavy water because it's usually generated and used in research sites for like government research or different applications that we'd have in research institutions, but it's not something you would find usually just out in the open where you might consume a lot of it. So it's unlikely that this would ever happen to you. Now let's consider ions. Let's define ions to make sure they're very clear what we're talking about. If I have an ion, I either have a single atom or sometimes a group of atoms that are bonded together that overall do not have the same number of electrons as the number of protons in the nucleus of that atom or the nuclei of the atoms in the group that we have. Okay, so this atom or group of atoms will have a net positive or negative charge because it has either gained electrons or lost electrons. If it has lost electrons, it forms a positively charged ion. If it has gained extra electrons, it forms a negatively charged ion. Okay, now ions are occurring because of having more or less electrons than the numbers of protons in the nucleus. Okay, now if I have a positively charged ion, as I said before, that means we've lost one or more electrons compared to the total that we began with when it was neutral. And in that case, we formed a cation. Now there's a few little mnemonic devices that can help you remember the charge on a cation. If you think about the T in the word cation as a plus symbol, that might help you remember that cations are positive. Okay. Another way that you might remember this is if you're a cat lover, you can think, well, of course cations are positive, right? Because cats have paws, right? Positive, haha. I know, that's a terrible joke. Now, if we look at anions, they're going to be negative ions. That means they have gained one or more extra electrons. So if we go ahead and look at anions, it's really easy to remember they're negative because you can think about it this way as your mnemonic device to help you remember it. It's A, and think of the N as negative, a negative ion, right? Anions are a negative ion or a set of negative ions. Right? So think of the N reminding you they're negative. Think of the T here reminding you that cations have positive charges. Think of it as a plus sign. That's going to help you remember them. So let's try to predict what's going on. Let's say we have a neutral bromine atom here. Okay, so if it's neutral, it should have the same number of electrons as its atomic number, which is 35. Because it has the same number of electrons as protons in order to be neutral, we have equivalent numbers of charged particles here, subatomic particles. So we have 35 protons, 35 electrons. Overall, we have no net charge in the whole particle. The neutrons don't contribute because, as their name implies, they're neutral. So if we have the bromine atom, if we were to lose electrons, we'd form a cation that's positively charged. So if we have less than 35 electrons, it would form a cation. If we gained electrons and end up with more than 35 electrons, we'd get an anion that was negatively charged. Now, bromine, just so you're aware, doesn't readily lose electrons. It usually will gain them to form anions. But if it were to lose an electron, we would see that the mass number doesn't change significantly enough because of the low mass of electrons. So we still treat it as 79. The atomic number changed. It's still 35 because we didn't lose any protons. But now we only have 34 electrons. So I have 35 positive charges and 34 negative charges. If I add up a positive 35 with a negative 34, we have a net charge of a +1. So the bromine cation would have a +1 charge because of the loss of 1 electron. You won't run into bromine cations very often in the course, just not very stable, doesn't happen very often, costs a lot of energy to do so. However, bromine often can gain electrons and actually become more stable. And so bromine, when it starts to gain an electron, will form an anion. Since I started with 35 protons to begin with, and I gain an extra electron, that means I ended up with having 36 electrons total. So if I take a positive 35 and add a negative 36, I have a net charge of a -1. So my bromine has formed a negative charged anion because it has 1 additional electron than it would have when it's neutral. Now we give a special name to nonmetals when they're part of a monoatomic ion. Now a monoatomic ion is a single atom that has gained or lost 1 or more electrons. So here we have a single atom, bromine, gaining 1 extra electron to form an anion. We give the bromine a new name when it forms an anion this way. When it's monoatomic, we call it with an ending that's an "ide." We change the ending of the element name to "ide." So I would name this bromide. Okay, so we see that with monatomic nonmetals when they form anions. So if oxygen were to gain 2 extra electrons, we would call that oxide. If sulfur gained 2 electrons, we call that sulfide, which is where we tend to have them stable. Now chlorine tends to gain 1 electron and it forms chloride. So when you hear that "ide," that frequently will indicate, especially if we have cations and anions in our formula, it will indicate we have a monoatomic anion most of the time. Okay, we'll talk more about naming in the next chapter when we name compounds. Now let's look at a few diagrams when we're forming ions. So here's a diagram of a magnesium atom where we've scaled up the size of the nucleus so we can look at the charges of protons and neutrons. The blue particles are positive protons, as their charge sign indicates. The red particles have no charge indicated, so they would be neutrons. If I were to count the number of protons and neutrons in a magnesium atom, we would find its nucleus, because magnesium on the periodic table has an atomic number of 12, has 12 protons. Now, if my mass number for magnesium was 24, that would mean I'd also have 12 neutrons. Now, if it's a neutral magnesium atom, we'd have to have 12 electrons outside of the nucleus, taking up the rest of the volume of the atom. Okay, it's actually part of what we call a probability cloud that we will talk about later. But we have the rest of those electrons outside of the nucleus. They have to be equal to the value of the number of protons in order to have a neutral atom. However, if I were to lose 2 electrons, so I only have 10 electrons, compared to the 12 protons that are still maintained in the nucleus, we would end up having a +2 charged cation, because if I take a positive 12 for the protons and a negative 10 for the electrons and add those up, we end up with a net charge of a +2. So I show magnesium with a 2+ charge for the cation. Now I want you to note, when we form ions, we aren't changing any of the numbers of the particles in the nucleus. The protons aren't changing. If they did, we'd have a new atomic number and an entirely different element. That's only going to be happening in nuclear processes, not in chemical reactions. So chemical reactions are going to involve just the outer electrons. Now, my neutrons are also maintained because I am not changing the number of neutrons in the nucleus. If we did have a different number of neutrons in the nucleus, we'd end up with another isotope of magnesium, right? Okay. So hopefully you can start to visualize what's going on with subatomic particles as we form ions. Let's try looking at one more. If I have a neutral nitrogen atom, well, the atomic number for nitrogen is 7, which would mean I have 7 protons. A very common isotope of nitrogen is a nitrogen-14 isotope, which would have 7 neutrons in the nucleus. Now, I must have 7 electrons if it's a neutral nitrogen atom, because if I take a +7 for the protons and a -7 for the electrons, it should add up to 0 if it's a neutral atom. Now, however, if I were to gain an extra 3 electrons to have total of 10 electrons outside of the nucleus, we would find when I add a positive 7 for the protons and a negative 10 for the electrons, we have a net charge of a 3 negative to form the nitrogen anion, and we change the ending. It's a nonmetal that's monoatomic, meaning just a single atom's involved with this nonmetal anion. We're going to change the ending to an ide, like we saw with the bromine forming bromide. Here we form nitride. So nitride tells me I just have one nitrogen atom that has gained electrons to form an anion. And if we look at the periodic table, it's positioned 3 away from neon. The nearest noble gas would indicate it would like to gain 3 electrons to form a negative 3 charged anion in order to become stable. Okay, we talked a little bit about ion formation and stability in our classifying of elements on the periodic table video, so if you missed that, go back and watch it again, and that'll help you out with chapter 3 as well. So these are some good skills that you're developing to help you in the future sections of the course. Okay, let's work a couple of problems to practice predicting the number of subatomic particles now that we have ions. You're probably very good at predicting the number of subatomic particles when you have a neutral atom, because the number of protons is equal to the number of electrons. And if I subtract my protons from my mass number, I can get the number of neutrons. Now, however, if I have a charge shown when I form a cation or an anion, when I'm forming ions, that would indicate that the electrons are no longer equal to the number of protons. So let's see if we can predict what's happening with electrons now and the other subatomic particles once we start to get charged ions. Okay, so here we have a cation. I know it's a cation because it's positively charged. Remember, the T in the name cation reminds you of that positive charge that we're seeing on the ion. This is the aluminum cation, and the only stable cation of aluminum that forms is a +3 charged cation. Now, as aluminum forms a cation, it's losing 3 electrons to form this stable charge. That's what it prefers to do. It doesn't like to lose any more or any less than that. So aluminum's always +3 when it forms a stable ion. Now, if I want to predict the number of protons, neutrons, and electrons, you're welcome to pause the video if you'd like to and try to write this down on your piece of paper and predict it before I give it to you. So do that now if you'd like. If not, I'll give you the answer to this one. Okay, so if I'm going to predict the number of protons, neutrons, and electrons, I usually like to go to my atomic number first, which is 13 for aluminum. If I didn't give you the 13, you look on the periodic table for aluminum and you find, oh yes, it's in period 3. And so aluminum has a atomic number of 13, and so that's equal to the number of protons. So I know there's 13 protons. If I subtract 13 from 27, which is the mass number, I would have the number of neutrons, which would be 14. Now, if this were a neutral aluminum atom, I would have 13 electrons, but it is not neutral. It's an ion. It's a cation. It has a 3+ charge. Now, remember, even though it's a positive sign on the charge, that's occurring because we're losing electrons. So that means I've lost 3 electrons. If the neutral atom would have had 13 electrons, the same as the number of protons, I would have had to lose 3 to only leave me 10 electrons. So the correct answer to this was 13 protons, 14 neutrons, and 10 electrons, 3 less than I'd have in the neutral atom because of the +3 charge. So remember, cations are losing electrons even though we have a positive charge. Negative charges indicate that you're gaining electrons. So with that in mind, let's look at our next example. So here we have selenium. Okay, if I didn't have the atomic number, I look on the periodic table, I find selenium has an atomic number of 34. It's an ion because in the upper right-hand superscript, I show a charge of a 2-. Now, it's a 2-, that's telling me what's happened with the number of electrons. So if you want to pause the video and predict numbers of protons, neutrons, and electrons, do so. Okay, if I had a neutral selenium atom, I would have 34 electrons, the same as the number of protons. However, if I have a negative charge, every one of the negative charges in my magnitude here is equivalent to have gaining 1 extra electron. So this indicates I have 2 extra electrons present. And that would mean if I had 34 protons and 34 electrons in the neutral atom, I would have to have 36 electrons once I have a -2 charge. 2 extra negative charges from 2 extra electrons as I form an anion, a negative ion. Okay, if I want to find my number of neutrons, I could subtract 34 from 78, and I would find that that would leave me with 44, so there'd be 44 neutrons determined from that mass number. So if you had the right answer, it was 34 protons, 44 neutrons, 36 electrons. There's 2 extra electrons because of that -2 charge. Now, this is a monoatomic ion. There's only one non-metal atom there, so it's an anion that is forming with this -2 charge. I know it's an anion because of the negative charge. Now, when I get monatomic anions with these non-metals, we predict the ending will be an ide. So I named this, instead of selenium, selenide as I form the anion. So the ending went to an ide. You'll notice with the cation of aluminum, we didn't change the ending of the name. We just called it the aluminum cation. So we used the same name as it was. Let's consider one more ion here. Now, I didn't give you the atomic number, but that shouldn't cause us much of a problem. If you go ahead and look at your periodic table for chlorine, you'll see chlorine has an atomic number of 17, right? We have an atomic number of 17 for chlorine, and so that gives me the number of protons, right? Go ahead and pause if you want to predict everything else. Now I can determine the number of neutrons by subtracting my atomic number from 37. So if I subtract my 17 from 37, that would give me 20 neutrons. The atomic number is 17, so that's my number of protons. It's an anion. It has a negative charge. If I don't show a number, we assume it's a -1, right? A 1 negative for the ion. So we're going to end up having 1 extra electron because of that negative charge, because electrons have negative charges, right? So that must mean I have 1 more electron than the neutral atom would have. The neutral atom should have had equivalent numbers of protons and electrons. And so when it forms an anion with a -1 charge, we have 1 more. So since there's 17 protons, there would have been 17 electrons until we gained this extra one. So we end up with 18 electrons. So we have 17 protons, 20 neutrons, and 18 electrons in this case. Now, if we look at this element, this is cadmium. So there's another element to make sure you know the name and symbol for. So cadmium, in this case, is the cadmium-113 isotope. If I look on the periodic table, I can find cadmium right underneath zinc. Now, the only stable ion that I predict to form with cadmium is a 2+, and so I end up with the cadmium forming a 2+ because it has lost 2 electrons. If I want to find the atomic number for cadmium, I look under zinc, and there's cadmium on the periodic table. It has an atomic number of 48, so I have 48 protons. I would have had 48 electrons until I lost 2 to form my +2 charge, so I should have 46 electrons left. And if I take my atomic number from my mass number, so if I take the 48 protons I'm reading on the periodic table for the atomic number from 113, I have 65 left over, so I'd have to have 65 neutrons. Okay, so now you should be able to name or predict the number of protons, neutrons, and electrons pretty readily for ions as well as neutral atoms at this point. We'll practice a couple more. Here's magnesium. Magnesium forms a +2 charged cation. And that occurs because it has lost, as we saw last time, 2 electrons. Okay, if I look at the atomic number for magnesium, now magnesium's in group 2. So it's in column 2 on the periodic table, group or family, that is named the alkaline earth metals. So magnesium is an alkaline earth metal. If I look in that group 2, the alkaline earth metals, it's right under beryllium, right above calcium. It has an atomic number of 12. And so we have, for magnesium, 12 protons. When it was neutral, it would have had 12 electrons, but it lost 2, so I only have 10 electrons left. If I subtract the atomic number of 12 from 24, that leaves me 12 again, so I have 12 neutrons in the nucleus. So 12 protons, 12 neutrons, and 10 electrons. Now, I want you to notice that all of these ions that I've looked at with their charges on this slide, these are the only stable monoatomic ions we expect to occur. So aluminum we expect to always have a 3+ charge when it's forming a cation. Selenium is always a 2- charge when it forms a stable anion. Chloride is always a -1 charge when it forms a stable anion. Cadmium is always a 2+ charge when it forms a stable cation. And magnesium is always a 2+ charge when it forms a stable cation. If you don't recall how we can break these charges, you should look at our video again on classifying elements. Go ahead and fast forward to the portion where where we're predicting ion charge. That's in the second half of that video, and that will help you practice those. So when I write symbols for ions, if I know the number of protons and electrons, this will help me write the symbols for ions. If I know I have 20 protons and 18 electrons, I should be able to predict if I have a cation or an anion, and I should be able to predict from the number of protons what element I have. So I go to the periodic table and I look for an atomic number of 20, which would be equal to the number of protons in the nucleus, and identify the identity of the type of element that I have. So if I look on the periodic table, 20 is an alkaline earth metal. That was right below magnesium. That's calcium. So I must have a calcium atom here. And since I have 2 fewer electrons than the number of protons, I have a plus 20 charge from the 20 protons and negative 18 charge from all the electrons. If I add up a positive 20 and a negative 18, I get a positive 2. So I get a cation, which is what we would expect for a metal. Metals usually form cations, and then we would end up with having a plus 2 charge on this metal because of the 2 electrons lost. Alkaline earth metals in group 2, we expect them all to form plus 2 charge stable cations. So I'd write this with the charge shown as upper right hand superscript with the number followed by the charge sign. So it's a 2 plus, meaning that I lost 2 electrons. Now if I look at our second example here with 16 protons and 18 electrons, if we go to the periodic table and look at the number of protons for an atomic number of 16 that I would have, I can see that my element here would be sulfur. So I have sulfur. Since the number of electrons is not equal to the number of protons, I must have an ion. And it must, since it has 2 extra electrons, be an anion because I have a positive 16 charge, a negative 18 charge. If I add a positive 16 plus a negative 18, I'm going to end up with an overall negative 2 charge. So sulfur here is forming an anion with a minus 2 charge. So I write the symbol for sulfur. In the upper right hand superscript, I indicate the magnitude of charge and the sign. So I always show the 2, then the negative is the standard way of showing this. It is actually incorrect notation to show the minus and then the 2. Show the 2, then the minus as I've shown here. Now if we look at our last example on this slide, we have 26 protons and 23 electrons. If I want to identify the element I have, I go to the number of protons. That's the same as my atomic number to identify which element I have. So if I look at the periodic table, 26 protons, that would be iron. Iron has an atomic number of 26. Since the number of electrons is not equal to the number of protons, that tells me immediately I must have an ion. If you're thinking, well, it's a metal, right? It's an iron atom, you maybe already are predicting it would probably form a cation. Okay. In this case, we also know that we have 3 fewer electrons, so we lost 3 electrons, which occurs when you form cations. So that fits what we would have predicted. So if I have a positive 26 from all 26 protons and a negative 23 from the 23 electrons that are still there, I would end up adding those 2 up, and I would have a positive 3 charge from the extra protons. So I have an iron cation with a positive charge of 3. Now iron can form several different charged ions. The most common ones you run into are the iron 2 and the iron 3 cations. When we write names of ionic compounds with these 2 types of iron cations, we use Roman numerals in their names to indicate which charge, whether it's a 2 plus or a 3 plus. So you'll be seeing that in the next chapter as we start naming ionic compounds. I recommend you start learning the names of your common ions off your common ion sheet so you're ready for our quiz that's coming up on Blackboard. Okay, so there's our iron 3 cation. We've now learned how to predict formulas of ions based on numbers of protons and number of electrons. Remember, always show your charge as the upper right hand superscript. When a nonmetal monoatomic ion, like when I have 1 sulfur atom, forms an anion, we end up having the ending of the nonmetal change to an ide. So this is sulfide. Here we just call this the calcium cation. Here I would call this the iron 3 cation to specify its the specific cation of iron that has a 3 plus charge. Since other charges are possible, I'd write its name with a Roman numeral later, or use an older fashioned name that I will teach you in the next chapter. Okay, so if we're looking at some isotope symbols, let's figure out which one of these isotope symbols would be correct in the case of having 45 neutrons, 34 protons, and 36 electrons. Now, if I have 34 protons, well, we know from looking at the periodic table that has to be selenium. All of the possible examples I gave here is selenium. If you want to pause the video and try to answer this on your own, please do so now. Okay, now I have 36 electrons. Since I have 2 more electrons than the number of protons, I must have formed an anion, because the extra 2 negative charges from the extra 2 electrons would give me a 2- charge on my symbol in the upper right-hand superscript. So the only answers that fit the bill there would be A and C, where we formed selenide ions. So the next thing I have to look at with those 2 possibilities is which would have the right mass number. Okay, now if I wrote 45, that's much too small for my mass number because I have 45 neutrons and 34 protons. I need to add them both up to be my mass number. So the correct mass number here would be 79. Since 2 extra electrons were gained, I have a 2- charge and an anion, so C was the best answer. So I hope you picked the right answer here. So at this point, you're pretty much a pro at predicting charges on ions. Okay, and the number of subatomic particles that are present in them. I think we'll pause here with respect to the discussion today, and next time we'll continue with looking at atomic mass and relative atomic mass, and then we'll also look a little bit at forming ionic compounds with ions balancing their charges. So we'll continue with that in our next discussion.